Ok, ¿estamos acá? Hola, hola.
Hello.
Did you guys have a good break? Tranquilo. Okay, I think we're almost to a quorum, so we can begin. Any questions? Doubts? No? Okay. So let's see, we left off last time talking about molecules and a variety of different sort of properties. And let me find my screen. So here I was going to give you a bit more in terms of the examples and the practical side of things, rather than the nomenclature. And right. And I'll actually go back a little bit because we didn't talk too much about a sort of neutral hydrogen and measuring the spin from neutral hydrogen. And the reason this is kind of important is because, I mean, obviously hydrogen is super abundant. And the key problem is that most hydrogen is in molecular form, but it's not really easily detectable. And this is because it doesn't have a dipole moment, so it doesn't generate any rotational lines. And those are the easiest to detect. The vibrational lines come out of the mid-infrared, which obviously means we need to have a very high sight observationally, or go to space to see it, right? So it's much harder to do, or it comes out in the UV, in the electronic lines. And again, there we need to go to space to do it. So in terms of what can we observe from the ground, we're kind of stuck because we actually can't observe molecular hydrogen from the ground. And so what we try to do is use neutral hydrogen to infer what the molecular hydrogen is doing. And that kind of works in some situations and it kind of doesn't work in other situations. So going into a little bit more specifics on neutral hydrogen, right, we talked again last time about how neutral hydrogen basically has this spin flip, which is a hyperfine line. And so the transition occurs at about 1420 megahertz or 1.4 gigahertz. And this is often why you have radio bands that are taken around 1.4 gigahertz, is because that's a key band to sort of optimize for galactic surveys or nearby galaxies to survey H1. So that occurs at 21 centimeters in wavelength. And it occurs from, you have a proton with a spin, you have an electron with a spin, and in general, when you get this spin flip, you have this change of energy. And so the two energy levels between this magnetic interaction allow you basically to, whether this is in parallel or anti-parallel. And so that emits that difference in energy emits a photon, which is related to this frequency. And so this frequency you can calculate, which is the ratio of the two masses, the absorption probability, and then this is the hydrogen Ringberg frequency. And then you have the statistical weight here. And actually, sorry, this alpha is not the combination. This alpha is just the fine structure combination. And so you can calculate what the emission coefficient is. And so the emission coefficient for this particular line, it's related to this, which is the dipole moment. And it's the magnetic dipole moment, right, because of the spins. And so this magnetic dipole moment is equal to this. And so it has a value of which is relatively tiny. Then you have the frequency, which is, you just plug that in here and you can evaluate what this emission coefficient is. And this emission coefficient turns out to be about 10 to the minus 3 times 10 to the minus 15 per second. And so we can think about the half-life of this transition. So the half-life is going to be the inverse of this emission coefficient. And so the inverse of 10 to the minus 15 is a very large number. And so, typically if you have some cloud of neutral hydrogen sitting there, all in the up or sort of elevated state, it takes 11 million years for half of those transitions to decay and emit a photon. So it's a very slow process in some ways. Many millions of years is kind of equivalent to dynamical time scales around galaxies and so forth. Or actually, I guess millions of years, yeah, it might be tens of millions of years for orbital time scales. And so typically the other issue here is because this is a long time scale, if you have any kinematics in the cloud, they're going to de-excite it, right? You're going to get a collisional de-excitation of the transition, and so you drop out. And so you need hydrogen in effectively, a very low density state in order for you to not have a collisional de-excitation. And so the critical density here is extremely low. It's less than 1 cm per cubic centimeter. So these are really diffuse regions of the ISM, can be probed by the neutral hydrogen. But really dense regions, which are typically what you would find in the central regions of galaxies, they're completely collisionally de-excited. You can't probe it this way. And so you need another mechanism to probe it. And this is where CO comes in, because CO has a higher critical density and actually measures denser regions. And so you can use CO, as long as you know the ratio of CO to hydrogen, you can use it to estimate what the hydrogen content is in the central portions of the galaxies. Obviously, this is a bit complicated because you want to get the entire gas content in hydrogen. You want to know that. It's just not an easy thing to measure. And so you need to do different tests in different regimes to collect all of the hydrogen that might exist in the galaxy. So regardless of whether this neutral hydrogen is an LTE or not, basically you can define a spin temperature. And this is the analog of the molecular excitation temperature that we defined in the last class. And so based on the Boltzmann equation, we have this ratio of the different, the ground state versus the elevated state of the spin, and it's related to the statistical weights. And then this is the spin temperature now and the frequency. Right? And so these statistical weights are the upper and lower spin states. And so G1 equals 3, G0 equals 1 in this particular case. And so if we have this situation where the frequency is less than the kinematics, typically this means that you can have a temperature up to about 150, which is not too bad. So cool gas, you can do pretty well. And so this works. And then the total hydrogen is the combination of these two. And so it's just 4 times the ground state. We can estimate the opacity here. And so the opacity is our emission coefficient, our statistical weights, the total number, and then our factor here, and then our line width. And so this, roughly speaking, if this is relatively low, we can Taylor expand this. And so this is approximately equal to this. We've plugged out and we've modified. This is now the ground state versus, and that's 1/4 of the total. And then we have, it's just combining these, crossing out some of the terms. This frequency gets eliminated here. And so we have something which looks like this. So it's just 1 over the frequency, 1 over KTS, the line width, and some constants. We can define this column density here. This is not the column density, this is the number density. And so the number density, we can relate that to the column density along the line of sight as just the integral. So we have the number density along the line of sight, that's usually the column density. And so it's typically the column density that you end up measuring. And then you have to make some assumption about how the distribution of densities may vary along the line of sight. So the total opacity here in terms of sigma for a sort of isothermal distribution of hydrogen, so it's all at the same temperature, will just then be proportional to the column density. And so as long as it's not optically thick, right, so tau is less than 0, then you see the entire distribution along the line of sight. And so if you just integrate the emission line in terms of a brightness temperature, that's going to be proportional to the number density, or and if you assume it's isothermally distributed here, it's going to be proportional to the density. And so this brightness temperature basically is proportional to this. It's independent of the spin temperature. And so you have something which looks like this. This thing is proportional to this, and so this is more or less sort of constant in this particular limit. And so what's nice is that you can get the column density directly from the line. You just sum over the line width, and that brightness gives you the column density. So it's a very straightforward, you have the integral of this brightness temperature over the frequencies that it might exist at, times that you evaluate all the constants, and that gives you the column density. Perfect. The only problems will occur when now you have tau equals 1. You're not seeing the entire thing, right? You're only seeing the sort of outer edges of it. And so then it no longer works, and so it breaks down. And that's kind of stating that this thing breaks down. And again, that comes back to sort of the centers of the galaxies. Okay. So in general, this absorption, typically what you'll see is you might have line emission, which comes from the gas. But if you have cooler gas in front of a continuum source, for instance, then typically the hydrogen will absorb it, and you'll get an absorption line. But the absorption line, again, will, so you're not measuring the brightness temperature, you're measuring an absorption feature. But that absorption feature, again, is going to be proportional to the column density along the line of sight, as long as you don't saturate the absorption line. Once you saturate it, meaning you go to 0, then it becomes more difficult to get out the true column density. I'll show you an example in a second. So this is, typically you have, here's something in emission, and so you might see this emission. This might be what you see in absorption from a continuum source. And so you actually, so imagine you have a continuum source here, and you observe absorption, and then around it, you see emission in this line. And so you can kind of tie these two together to understand which portions are optically thick and which portions are optically thin. And so like this portion seems to be optically thin, but maybe this portion here is optically thick because you don't get a strong brightness even though you have a huge absorption depth. And so using these two sort of techniques along similar lines of sight, you can kind of understand what's going on in this. And of course, then the velocity structure here means that the hydrogen is at a certain radial, a Doppler velocity from us, which means it's either moving towards us or away from us. And so you can map that out, and you can then map the rotation of our galaxy, for instance, or a rotation of a galaxy outside of the Milky Way. So this equilibrium temperature of neutral hydrogen in the ISM is a balance of heating and cooling. And the primary heating source of the diffuse ISM is going to be cosmic rays and UV photons from hot stars. And so you typically will have, you calculate what's the ionizing sort of distribution of photons from stars, and then what's the cosmic ray distribution from supernovae and whatnot. And this is typically harder to estimate. You can kind of estimate this from radio emission, from synchrotron, which we talked about before. And so you can relate it, the synchrotron emission, to some distribution of cosmic rays with a distribution of energies. So the main coolant that we talked about on last Wednesday was singly ionized carbon, so C2. And so this is typically the way that most of the ISM cools, because this has a relatively fast transition. And so there are some other ones that are also important from nitrogen and oxygen. So this line ends up being strong only when the temperature KT is at least H nu. And this means that the cooling rate here increases exponentially above this relation. So T will be proportional to this, and so we can evaluate this. And so generally when you have temperatures well above sort of 90 Kelvin, then this emission line starts to pop up pretty strongly. And so typically we can measure the actual kinetic temperature of neutral hydrogen in the galaxy using the hydrogen line brightness. And so in the places where it's optically thick, right, so going back here, if it's optically thick, then TB is actually going to be related to TS, because we're only seeing the outer edge of this material. And so then we have an estimate for the optically thick regions of what TS is. Whereas in the optically thin regions, TB just equals, or is sort of constrained by the column density. So that allows us to kind of understand the variation in the temperature and the density. And we can estimate, in general, the brightness temperature will approach this excitation temperature. It'll be close to kinetic temperature, LTE. And so we have many, many lines of sight, and we can kind of estimate this. And typically you can have brightness temperatures that get up to about 100, 150. And you can actually confirm this with dust. And so the dust temperatures, if you observe dust, it has this gray body spectrum, and the typical temperature is kind of going to be of the order of 50 to 100 Kelvin. And so you can kind of confirm this. Unfortunately, the field of view, not the field of the beam size of infrared telescopes has not been that great compared to ground-based telescopes for H1, so you have to match the beams and everything to be sure. But anyway, there's the point here is there's a temperature-dependent cooling. You can kind of get at it by comparing the different emission lines that you see, or the different emission and absorption lines. Okay, so coming back to the fact that we can, we see different velocities along the line of sight. You can, if you have a model for the Milky Way, for instance, and you say, okay, we have a model of the velocity profile as a function of radius, and we're looking along the line of sight. So let's say, I guess we're here, and we're looking at all of these things along the line, or actually this is the sun, and we're here moving this way. We see the galactic center, we see two lines of sight, and these different clouds are actually they have the same Doppler velocity moving away from us. And so the only confusion is when you get something like this. So for all the other lines, right, so there's always going to be some component here which is confused with some component here. And you have to make some estimate of what contamination you're going to get. Obviously, the clouds here that are having emission lines are going to be stronger than here because this distance is twice as much, right? But in terms of the absorption doesn't really care. And so the absorption, if you see it in absorption, you're going to see equal amounts just depending on the column density from here and here. So nonetheless, you can kind of piece this together and get a radial profile of the velocity structure, assuming that things are sort of symmetric, right? That you have a velocity profile which is radially symmetric in the disk. So that's more or less what you can do. The benefit of this is that the hydrogen going to the radio is optically thin. So for the most part, you will have, except for very dense clouds, which will sort of measure the emission will, the radio continuum emission from this background source will be able to travel through without being absorbed. And so you can see all the way through the galactic disk, which is a benefit versus, say, stars, where the disk is obscured in the optical, and we can barely see around the local neighborhood. And then when we go into the K band, for instance, we can see into sort of the galactic center, but the things behind the galactic center become pretty faint. And so it's difficult to really piece that together. So much of what we know about the velocity structure of the Milky Way originally came from H1 studies. And this is just showing sort of how you would calculate the sort of minimum radius and then understand the velocity structure based on that. And so typically at, say, a velocity, a longitude of about 30 degrees in galactic longitude, the terminal velocity is of order 130 kiloparsecs or so. And it has a pretty flat sort of distribution. So it rises up here, is sort of flat, and then has some wiggles, but then we'll go out further. Okay, so another thing one can do is obviously if you can measure the column density and you can estimate something about the size of the source at that particular velocity, then you can turn that into a density. And if you know the size, you can turn that into a mass. And so generally speaking, if you think about it, okay, we have a certain beam and we have a certain amount of emission that fills that beam, then you can kind of turn that into a mass. And so that's what this equation is looking at. And so we have redshifted 21 centimeter, and we have galaxies which are unresolved by the single dish radio astronomy, the radio dishes. And so just as an example, so the 100-meter Green Bank telescope has a 4 with absolute 9 points. And so only the nearest galaxies are going to be resolved by that. And so you point it at a nearby galaxy and you get all the H1 from that galaxy in line emission, your absorption, or from the background continuum, or the continuum within the galaxy from the synchrotron, or you see it in emission. And so if the emission is optically thin, which is a decent assumption, then you integrate that flux, and that allows you to estimate the mass of this galaxy. And you don't need to know the temperature or anything, where you assume that the temperature is below some sort of critical value like 150. But other than that, you can kind of convert a flux over the line width, and assuming the distance, you can convert that into a mass, which is pretty cool. And so this gives you the mass of neutral gas, and then you would have to make some assumptions about how you convert the neutral to the total, which are not necessarily trivial, but can be done. You also want to make corrections for, if you have disk inclination and what the galaxy mass is, or the morphological type. These things kind of correlate with some ratio of opacity. So some of the hydrogen is going to be optically thick, some is going to be optically thin, and so you can kind of correlate that and calibrate this. When you're able to actually resolve the H1, then you can actually do spatially resolved kinematics, which are cool. So you can measure the mass enclosed within a certain radius, assuming some sort of the velocities are based on some model of the galaxy. Right, so if it has a circular orbit with a characteristic velocity field, you can use that to estimate what the total encircled mass is. You also have an estimate of the neutral mass and maybe the total gas mass. You might be able to estimate the stars, and therefore then you can characterize how much missing mass is there and relate that to potential dark matter. So this is just an example of this. This is what's called a spider diagram. And so this is color-coded, but it's a velocity distribution here. So you see that the red is moving away from us, the blue is moving towards us, and then the middle portion is not doing, right, it's sort of in between. And so this is this galaxy here, and then this is the velocity distribution as a function of declination. This is the density of hydrogen. And so you can see that it sort of peaks here. And then this is color coded, this spider diagram, which is inverse of this one. This is M33, this is UGC 11707, just to give it out. And then this is the overall emission of this galaxy. Okay. The benefit of being able to measure neutral hydrogen is you can actually trace the gas. And so something which looks like this and doesn't look like it's interacting at all, when you look in hydrogen, you see that actually it does look like it's interacting. And in fact, you see tidal streams and all sorts of extra information about the interactions. Here's another version of this. So this is the antennae, and this in blue is the hydrogen tail. All right, so you can see the stellar tail is very faint, but the hydrogen tail, you can see it out to very high distances, very large distances. Okay. So the point of all that was how do you measure most of the gas, and how then do we make a correction for H2, since actually a large fraction of the hydrogen will end up being in H2. And hydrogen dominates it over anything else. As I mentioned, H2 is homonuclear, no dipole moment, no rotational transitions whatsoever, and so only see it in vibrational or electronic. And so the vibrational turn out to be around 6 micron, and they have this, remember this ladder structure where you had the R band and the S, let's see, it was, I have to remember them. There was an R and an M band. I have to go back and look. And then then that was for J equals 1, and then you had J equals 2, which was an S and O. So maybe it was R and P. Yeah, because it was around Q. Q is 0 transition. R is +1. P is -1, and then S is +2, and O is +2. So around 6 micron, but I think the R version of that bleeds into the 2 micron band where we can observe it. The problem here is that another problem with the vibration is that dust emission is super strong. And so you have a high background. So these lines are not very easy to measure. And you have to go to space to really measure 6 micron. The alternative is these electronic transitions, which are, typically we see them in absorption against UV stars. And these are known as the Warner bands. So this is an example of, this is a Spitzer spectrum of, this is shocked H2 from the supernova in G357. And so you can see these are the different vibrational transitions here. And so this is, again, 6 micron all the way up to 30 micron. And these are a couple of extra sort of examples from, this is now spiral galaxies in Virgo. And these are, again, shocked excited. And so you can see they're very faint, right? Here, this is a little bit brighter. This is pretty faint. There are much brighter emission lines. There's PAH features here. This is a PAH feature. And so they're very tricky to measure correctly. You have to model the continuum and so forth. This is the UV, and this is a UV star, and then these transitions here are some of the Warner bands. And so you can see that, again, they're that's iron, sorry. So here and here and here, you can kind of measure them. But it's not trivial. You need a good spectrum to do that. So this is an example against the SMC, which is a relatively metal poor ISM. And so these things, you can see these in diffuse ISM as well as in clouds. Here's another example. This is from Rho Fucus, which is a star-forming region. And here it's really quite dense. And so you can see that the lines have actually saturated. And so that then is difficult to measure because you don't know exactly what the optical depth is. You can kind of estimate it from from this portion of the line and this portion of the line, but you have multiple combinations here. So it's non-trivial to back out a unique solution. So typically for these electronic transitions, you have this observation. This is going from j equals 1 to, say, j equals 1 to j equals 0 transition. So this is a rotational transition on top of the vibrational one. And so typically here, this ratio is going to be dictated by this temperature balance here. And so the typical temperatures in diffuse media will be between 45 and 150 or so. And so this ratio, when you go down to low densities, is going to be non-thermal. And this is sort of problematic for estimating things. And so typically the molecules will have a tendency to go to high J states. And then sort of relaxing VFO excitation. And so the thermal ratio tends to only be good for very low density regions. So 10 to the 18 or below. To give you an idea, if you look through the Milky Way, the column density along the Milky Way is about 10 to 21. And so, okay, obviously this is in cubic centimeters, so it's, most of that, sort of through the Milky Way, this would probably be pretty reasonable, because this is, so 10 to 21 cubic centimeters. If you then talk about 1,000 centimeters, that's nothing, right? So most of the Milky Way would be able to be probed by this sort of thing. But dense clouds like Ophiuchus, no. Okay, so as I said, most clouds consist of H2, and obviously you have other constituents that are in the cloud. And in fact, some of the molecular hydrogen will form on dust grains. And in fact, the dust grains will act as a catalyst for forming molecular hydrogen. So you'll have one hydrogen that will collect onto it, and you'll have another hydrogen, neutral hydrogen, and then they'll actually bond and then pop off. And so it's actually, dust grains are a very important catalyst for the production or the transition between neutral hydrogen and molecular hydrogen. And so you don't need too many of them. So generally effective production here requires some sort of minimum density of dust, which is about 50 dust grains per, or I guess, I think this is assuming some sort of metallicity. This is about 50 hydrogen atoms per cubic centimeter. So it's relatively low. So the molecule will be dissociated by relatively hard UV photons, so anything above 11 eV. And so if you see H2, you generally need to have something which shields it. And the dust grains actually act as a good shield as well. And so you have this complex process of dissociating the molecules, being able to sort of combine them again with dust grains, having the dust grains shield them, and so forth. So, the ISM physics are not trivial. Okay, so these constituents here, generally this dissociating radiation can actually penetrate pretty deep into a molecular cloud. And so generally speaking, you start to see molecular hydrogen around 10 to the 20 in this sort of regimes, which contrasts with this, right? So generally speaking, when you're in the regime where you're below 10 to 22, you're in a regime where you're going to be suffering from what exactly is the interstellar radiation field, how many photons are above 10 or 11 eV, and so forth. And so it's tricky to really constrain what's going on based on the column density of H2, for instance. And so you really also want neutral hydrogen. So this column density is about a visual extinction of 0.1 mag or so. And thinking about clouds. Generally speaking, a molecular cloud might consist of about 63% H2, 36% He, and about 1% dust. And then just trace other, few less than 1% other molecules and atoms. And just to sort of move on from that, these trace amounts of molecules and atoms, because they can be measured in the radio and submillimeter and millimeter bands, end up being very important tracers, even though by mass content they're tiny, right? They don't make anything, and so there's huge uncertainties between converting between the number of molecules of some species and hydrogen, right? Which also depend a little bit on where you're observing it from, because obviously if it's diffuse emission or very diffuse gas, you're going to have problems with the interstellar radiation field as well. So the study of molecules generally is much more complex than neutral hydrogen, because you have situations where you can deviate from local thermodynamic equilibrium. And so the populations generally, you characterize them by these excitation temperatures, which we talked about in the last class. And so the populations of a given species are generally specified by a range of excitation temperatures, depending on the transition. And so that's a little bit complicated. Well, actually, it's very complicated. You also have the problems with chemistry and how you deplete certain grains, certain atoms or molecules from the gas as they settle onto grains. And so you can have certain portions of that molecule kind of be hidden because they've formed more complex molecules. And this is not necessarily super easy to back out. And then you also have structure in everything, right? So it's not just a homogeneous uniform density medium, but you have different densities. You might have different temperatures. Those inhomogeneities are sometimes important, and you sort of average them out when you don't resolve them, and then you can get led to different interpretations if you don't account for these inhomogeneities or the degree of the inhomogeneities, which of course relate back to the interstellar chemistry, relate back to the deviations from LTE, and so forth. Okay, so not to dissuade you too much from this, I'll show some examples of some things you can do with them that are useful. So this is just a look at various molecules and their rotation ladder. So this is in terms of Kelvin. This is in terms of the frequency, and so you can see that typically radio observations are typically probing down here. Millimeter observations are probing sort of in here, and then submillimeter are probing in here. And so a lot of these things can be probed in the millimeter in the J1 transition. And then you need to go to the submillimeter to see higher excitation densities. These are just some of the most common tracers. So CO is very abundant. HCN traces dense gas. HCO plus traces dense gas. This is a sort of different version of HCN, HNC, so it traces slightly different things. You have ammonia here, and so forth. These are all of the different molecules, and I think this is probably not super complete, but these are all the molecules that have been confirmed and detected as a function of 2-atom molecules, 3, 4, etc. And obviously, as you get higher and higher, you eventually just bleed into different types of dust grains. And so when you look at a very sort of gas-rich region, this is Orion, the Orion bar region, you can see that the spectra is very, very rich in terms of, it's got many, many bright lines. So the red ones here are CO, and they're CO of different isotopes. So this is CO, C18O, C17O, this is C16O, etc. And so you see they're very, very bright. And then you can see other so HCO, you can see para water here. Then there's a neutral carbon line here, and so forth. So it's very, the spectra can be very rich, but also note that we're looking between, this is in microns now, so between 200 and 600 microns, which is a huge bandwidth, which is why you can see these multiple species from J values of 5 to 4, all the way up to 13 to 12 or so. This is a spatial version of looking at each of these lines. And so this is 12CO. This is the 9 to 8 transition. This is the 13 to 12, the 12 to 11, and this is 12CO versus 13CO. And one thing to sort of note here, this is a spatial direction, this is a velocity direction, or velocity component. And so you can see that 12CO peaks right around here, and the actual source that they observed was at 0. And if you go into 13CO, you notice that it's super bright, but it's not bright at all in 12CO. And this is because it's optically thick for 12CO. And so all you're seeing, you're not seeing the internal portion of the gas, you're only seeing the edge in 12CO. Whereas 13CO, because it's less abundant, the optical depth is lower, and so you can see all the way through. And so that's why this emission line is much stronger. And you see that for this, this is 13, 12, 10, 9. So you actually would want to compare these two in particular. So you can actually see that this is really very, very dense. And there's actually a clump here that is also missed here. And the velocities are also different, right? So the offsets here, this is at sort of 5 kilometers per second, whereas this is at 0. And so all of this is optically thick too, right? So it goes like that. And you can kind of see a difference, a transition as you move to lower J values. You see this kind of peaks up a little bit. And this is I guess the 0, but maybe this is from 1 to 0 then, to see some of this extra stuff here. Okay, so CO is a very powerful tracer because it's one of the brightest lines. So even though CO isn't typically that abundant compared to neutral hydrogen or molecular hydrogen, it turns out that in terms of its brightness, it's one of the brightest emission lines in the millimeter band to track things. And it traces really relatively sort of medium density structures. And so rather than trying to observe this, which you have to observe from the mid-infrared or in the UV, you observe other molecules like CO, CS, or HCN, and you infer what the density of molecular hydrogen is. So CO is nice because it has transitions at 1.3 millimeter and 2.6 millimeter that are the low J transitions. As I mentioned, it's much less abundant, but its A coefficients are very, very large. And so at tau equals 1, the CO column density is about 6 times 10 to the 15. And the CO abundance ratio is roughly about a factor of 10 to the 4. And so the amount of neutral hydrogen is roughly, almost a factor of, I guess, about 2,000 or 3,000, 2,000 different. So this amount of CO is compared to this amount of neutral hydrogen. So it's a little bit more sensitive than the spin line might be potentially. And this column density is about what the average column density ISM through the Milky Way is. Now, typically you can't use CO to look at optically thick clouds because this problem here, it becomes optically thick, and you can't use it to measure the total mass. You can only use it to measure the temperature, the excitation temperature. And so generally you use isotopes, which are less abundant. And so therefore the optical depth goes as the number density of that particular molecule or that particular species. And so the fact that it's less abundant means the optical depth is going to be lower. So 12CO is optically thick. And so if you don't have any background continuum sources, the excitation temperature is just determined then by the line. And so you can, in the optically thick regime, this brightness temperature, generally speaking, converts to an actual excitation temperature, which you can measure. And the excitation temperature, as long as there's not a huge variance over the cloud, which it might be, you can kind of use that to infer what the 13CO temperature might be. So in terms of using these isotopes, so 12C16CO is just 12CO, 13C16O is 13CO, and then 12C18O is C18O. And these are some of the more common molecules. And the ratio, the abundance ratio of these is about 500 to 70 to 1. So for one of these, there's 70 of these, and there's 500 of these. So this ratio here is roughly about a factor of 8, or maybe 7. So because they have a slightly different nuclear structure, the emission lines or the line transitions are slightly different. And so they're based on the mass ratio. And so the 1 to 0 transition for 13CO is about 5% different from 12CO. And so it occurs at 110 versus 115. And depending on the receivers, if the bandwidth is such, you may be able to get both in the same observation, which then is super useful because you have both together and you can measure, when one's optically thick, typically the other one might not be. And so you can measure the density from 13CO, use the abundance isotope ratio to get the total number, and then use the temperature measurement from the 12CO that's optically thick to get a handle on the overall physical situation. And so for the lower abundance 13CO, for C18O, generally you probe much deeper into the cloud, and you can use the optical depth here to get the optical depth for 13 and get the total number of 13CO, which is just given by this sort of formalization. And then plug it back in to get this, and then plug this back in to get this. So it's a little bit complex. There are big errors on each of these, but you can do it. And so going back to this plot and kind of reinterpreting it, right? You can get the column density from this. You would be able to get the temperature from this, although it's not really well detected. And likewise, you can more or less get the column density from most of these. I will note that there are some situations where even 13CO is optically thick, and then you would want to go to C18O for this extra factor here. And so things can get complex and they're really the hearts of the clouds. So once you determine the number density here, you infer this, and this ratio here is often denoted alpha CO. And so you have basically a conversion factor. Unfortunately, this thing here is not universal, and it can be off by factors of several. And even once you start studying different types of galaxies, different types of galaxies seem to have a different conversion factor. And so things like the SMC which are really well studied, have an alpha CO of, I think about 0.5 or so. And then the EULERGs have an alpha CO of 4. And so there's almost a factor of 10 difference between, right, the factor of 8 difference between those, which makes things a bit complicated. So comparing the number densities, for instance, of 13CO to the number of molecular hydrogen, you have a range typically between 0.5 and 2 times 10 to the minus 6 here in terms of the number. This is slightly different from the definition of alpha CO, just to be careful with this. And so generally speaking, the way you would constrain this ratio is looking at UV data, or so the electronic or the vibrational transitions, and then looking at the rotation transitions here to calibrate it. And so this may be different in different places, hence this ratio. A big problem is that CO is generally not an LTE for higher J transition, higher J values. This ratio here and this ratio can be affected by a process called estration, which is the passage of the ISM through stars, or as stars are passing through the ISM, you can sort of change these values a little bit. And this ratio here basically could be a factor of 20 at the galactic center, but it could be much larger at galactic radio, like where the sun is. And so obviously this is a huge factor, right? So this comes into this big uncertainty in converting from say 13CO to 12CO and 12CO to hydrogen. You also have issues with what your assumptions are about if there's clumpiness in the clouds, if there's shadowing, and so forth. And then the isotope ratios could also vary, right, depending on exactly what the nucleosynthesis processes within the clouds, the metallicity that populated the clouds, and so forth. And so generally speaking, these indirect tracers can only constrain the H2 mass to factors of a few, and I think I'm being very generous here by few. Probably a factor of 5 or 10 might be more realistic. Okay, I think I've covered this portion. Are there any questions so far? Okay, I'll take that as a no. All right, so you can look at, this is actually a comparison of, this is now XCO, which is a slightly different parameterization of alpha CO. You see all of these in various forms. But this XCO is actually the ratio of the number of carbon to the number of, or I guess the number of CO to the number of molecular hydrogen. And this is per volume and per line of sight as well. And so these are our different curves for, so there's the dashed one, which is the ratio of 2 to 1 versus 1 to 0. And then there's the solid one, which is just the 1 to 0. And this is for a temperature of, a kinetic temperature of 10 Kelvin. And these are then different ratios of, let's see, what do I want to say? I think, let's see, this is it ratio, or I think this might be for different. Oh, this is for the strength of this line in some unit. So these are for a value of 6, for a value of 4, for 2. So this is roughly speaking sort of 1.5 orders of magnitude here. And then you can see how this ratio changes versus this. And so there's a strong sort of relation. So for a given line, you would measure this, and then it's not unique. And so this is sort of problematic. So you want to measure a couple of different lines and look at where these lines cross, which is why this thing looks so complicated. And then it changes as a function of temperature. And so you can see that these things will shift and move up here a bit. And so the idea is that if you measure enough J lines, you can pin down, roughly speaking, what the range of temperatures is, and then you can kind of convert that that number density of CO into a molecular hydrogen content. You can also use the CO lines. So this is just looking at the different transitions of CO from 1 to 0, 2 to 1, 4 to 3 with different telescopes, which have different beams, which are shown here. And you can see the velocity structure of them. And so here you see that it's relatively narrow velocity because this is cool gas. So it's mostly on wider scales. And as you go deeper in, you get to gas, which is maybe more rotationally dynamic. And so you see that the higher transitions, which are probing the central portions where things are a little bit hotter, you see that you have higher or broader lines. And so these are probing the internal portion of this protoplanetary nebula in this particular case. And you can see that there are some complications here where you have clumps maybe, which might be in the line of sight, which are, or maybe multiple components, which are leading to this velocity structure. This is looking at the different J values and the flux of 12CO and 13CO. And so generally speaking, you could take something like this, measure the total emission strength here, and then plot it. And typically you see that for a given density of material and a given sort of statistical weight and excitation temperature expectations, you would have one population with a density of 10 to the 3.5, which would, if it was just that gas, you would see an excitation curve, or this is called a CO sled, so a emission line diagram. And you would see something that would look like this. And so because you see this here, and then you see something which is, you see higher strength, high J value lines, you need multiple components. And so multiple densities to model this correctly. And so you can do this both for the 12CO, which might be somewhat optically thick, and then you could do this for 13CO. And the idea is, these should be, if you have some knowledge of the abundance ratio, the isotope ratio, you should be able to pick out exactly what's going on and kind of model this as a couple of different density components. And this sort of modeling is sort of done. It can be done in a departure from LTE, but you need to model both the temperature and the density. And this sort of approximation is often called the large velocity gradient, or LVG approximation. And so you'll see this in various places. So people have been observing CO for quite a while, and so there are maps at relatively low resolution of much of the galactic plane and the LMC and the SMC, and then there are higher resolution maps of Orion, Fuchsius, and so forth. And so CO maps are generally clumpier than, say, neutral hydrogen distributions. So there are also maps of neutral hydrogen made with radio, 21 centimeter, and in general, the CO maps are much clumpier because the neutral hydrogen, remember, was only measuring the low density portion of the ISM. The CO maps are measuring a much higher density portion, so much clumpier. So they measure individual molecular clouds, cloud complexes, and so forth. And you can kind of take advantage of the variation between the velocity and the galactic radius to pick out different portions that might not be the same cloud. CO studies are generally very crucial for studying star formation because those are very dense molecular clouds, and also are very important for studying internal galactic structure where the densities and the temperatures are typically not in a regime where neutral hydrogen is accessible. And so it's important to do both to measure. So neutral hydrogen typically traces the outskirts of galaxies, and CO typically traces the central portions. And so CO surveys generally help us refine our understanding of spiral structure in concert with the H1 maps. So this is just an example of some nearby molecular clouds. So this is just showing, this is coordinate space here in L direction, and then flattening everything down in galactic latitude. And so these are the, we're sitting here. And so Orion is in this direction. Cygnus clouds, Cepheus are here, Perseus is here, so forth. I think there's the Taurus region, etc. And then these are the masses of these clouds. And so you can see a couple of very massive clouds, and the nearest thing like Taurus, Chameleon, those are all very tiny mass clouds. This is an example of Orion, looking at CO, and generally speaking, there are like OB associations, and so the O and B stars, some of them are kind of near the molecular components, some of them are far away, and so these are irradiating portions of this, and so you get shock interactions and interesting chemistry that comes from this. The trapezium cluster is hidden down in here somewhere. This is the Taurus region, and so again, you can see various molecular clouds, some of which are not very well probed by CO, 12CO, so you need 13CO as well. This is the Taurus molecular cloud, so this is this region here in higher detail. Right, so now with a 50 arcsecond beam, and you can see all the structure in here. You can do all sorts of fun things with dynamics. This is in 13CO. So just comparing these two, you can see there's lots of dense gas here, which is not so obvious here, right? I mean, it's brighter a little bit, but not nearly as bright as here. And so you need the two typically to really understand the molecular clouds. Again, this is a comparison of the young protocluster in Perseus, and here you can actually see jets from young protostars that are plowing away at some of this ISM, molecular gas. Beyond CO, there are other useful tracers, and so one of those is ammonia, which is shown here. So this is the emission ladder for ammonia, and this is ortho ammonia. So ammonia has para and ortho modes for the different rotation axes, and so which can be shown here. And so this is just for I think this is just the ortho mode. And so there's another wing here, which would be the para mode, which has slightly different energy levels. And so this is in J and K values here, and showing just the transitions. And this is in temperature now. And so these have lots of emission lines and can potentially be useful tracers of different aspects of the molecular clouds. So this is water showing the ortho and para. And so you can see there are slight difference in energies, not huge differences. And so you can use those to understand something about the magnetic fields, but potentially in these, or how things spin and how the cloud might interact with that. Then finally we have masers, which I sort of promised Laura I was going to talk about. And so masers, generally speaking, you don't see many atomic masers. You only really see molecular masers. And so the idea here is that we have these detailed balance equations, which give us spontaneous emission versus the spontaneous absorption, and or I guess spontaneous absorption. It should be so stimulated emission versus spontaneous. Or sorry, is that right? Yeah, stimulated emission versus spontaneous decay and absorb. Forgetting the word for it. It's not stimulated. It's just regular absorption. So this is the lower to upper versus upper to lower, so which you get from Boltzmann, and then you have the upper to lower versus the upper to lower here, which is given by this frequency ratio. These are the Einstein equations, and so the idea here is you can relate this to the column density and plug in this thing in terms of just the emission coefficient, for instance. You can understand what's going on with the system. So the issue with masers here is that we sort of have three processes. One is the absorption from the lower to upper level of the photon, and that increases the energy. Then we have the spontaneous emission, which we talked about before, and then we have the stimulated emission, which we had not treated before. And so basically the stimulated emission, ideally we treat this as a negative absorption in the equations here. And so when we talk about the net absorption coefficient, we talk about it in terms of this ratio, this difference here. And this difference is related to the upper and lower number densities. And so if you're able to populate the upper levels, then you can potentially, or the way you populate these can lead to the emission of photons. And so the ratio between the emission and the absorption coefficient, so the emission coefficient looks like that. The ratio of these two things is given by this, and so it's the ratio of this upper to lower. And the point here is then if you have LTE, then this ratio here is equal to the Boltzmann, and so the Boltzmann is equal to that, and so you can relate these things, and so this upper and lower level is just given by this, and so then the absorption coefficient should only look like this thing here, right? So we can, generally speaking, we've derived it in terms of the spontaneous emission coefficient. And the point here is that the positive term 1 comes from the absorption, and this exponential term comes from the negative opacity of stimulated emission. And so generally speaking, this thing is positive and we're sort of happy. However, this thing here, this negative exponential term, represents this negative opacity of stimulated emission. And so if you have a situation where this thing is much, much greater than that, then roughly speaking, the terms this thing should be equal to that, it's fine. And so the point here is that in certain situations, you can have stimulated emission that will cancel the absorption or significantly reduce the net line opacity. And so this thing here, the absorption coefficient is proportional to 1 over T, if you expand this out. And this thing is then proportional to a constant. And so if you have a situation where the source is optically thin, so tau is less than 1, the radial line emission is proportional to the column density along the line of sight, and it's independent of this temperature. So if we have something which is not an LT, then we can still define something which looks like this Boltzmann ratio, but this temperature now is not the LTE temperature, it's just this excitation temperature. And so if you have a case where you've somehow overpopulated the upper level, then this upper level ratio could be greater than this. And so what this ends up meaning is that this has to actually be negative in order for this to work. And then this thing also has to be negative. Right? Because if temperature, this excitation temperature turns out to be negative somehow, it's not physical. But if you're able to get a situation where the excitation temperature is negative, this is positive, this becomes very, very big, and then this becomes negative. And this yields this negative opacity coefficient or absorption coefficient. And so instead of you getting a loss, you end up getting a brightness gain. So you have an emission line which comes out. And this is known as a maser, right? So microwave amplification by stimulated emission radiation. And generally speaking, what has to happen here is that you have to have sort of, these frequencies are going to be much less than KT. And the brightness temperatures in this case can end up appearing, the brightness temperature is different from the excitation temperature. Remember, the brightness temperature of the line can be huge. So you can get brightness temperatures of the line of 10 to the 15 K, which are not physical, right? You are not going to have a temperature of 10 to 15 coming from the sort of accretion disk of an AGN. And so that's a sort of telltale sign is if you have line emission that has this brightness temperature, which is much in excess of what's sort of physically feasible. And you have the optical version of this is the laser. And so there are certain situations which can lead to this inversion of temperature. And typically in terms of astrophysics, these are called super radiant emission sources. And this is to distinguish them from laboratory sources. And so typically the most common astrophysical masers are water, or hydroxyl, or methanol, or formaldehyde, or silicon monoxide. And so what happens here in water molecules, you can see them in star-forming regions. And somehow you end up getting them into a population inversion where you're able to pump the upper level, right, versus the lower level. So you drive this situation up somehow. And in doing so, then you set up this process of stimulated emission. So one of the more common water maser lines is at 22 gigahertz, which is approachable from radio telescopes. And there's another one at 96 gigahertz, which is approachable with millimeter telescopes. And so these are some of the two more common, brighter maser lines that you can measure. Then you also have the fact that you can, so typically masers will be seen in molecular clouds, comets, planetary atmospheres, stellar atmospheres to some extent, and in some conditions the ISM. But then you have masers which are even more powerful, which are typically seen from the accretion disks of AGN. And they're typically, the AGN typically have an increased emission by about a factor of 1,000,000. So these are called megamasers. And so the difference between astrophysical masers and laboratory masers is that you don't set up a cavity for the maser, right? The astrophysical situation, you don't have this cavity. And so typically what happens is you only have a single pass through the medium where you're able to amplify the signal. And so you have to have these very particular lines of sight. And so one example, which is sort of good, is that you have somehow you've generated a density invert. Say you have an accretion disk going around, right? And so you have the situation where you have a velocity gradient across as a function of radius. And so as this thing is coming out, you will be seeing slightly different velocity structure, and the temperature structure is also a gradient. And so that will set up a population inversion where you can get stimulated emission along the disk of the AGN. Right? You contract all the density into this really thin disk, and so you get the mazing that goes all along the disk as this is coming out. And so, this is sort of in the outer portions of accretion disk. They obviously can't be too hot, or else we wouldn't have the molecules to do the mazing. But in these outer portions, you can set this up. And so for star forming regions, for instance, again, it's certain orientations. For instance, if you have a jet from a protoplanetary disk, and then you may be able to see masers along that jet because, again, of this gradient structure that you see. Now, the simple existence here of an inverted population is typically not sufficient, and so what the idea here is you need velocity coherence, and this is where the jet structure or the disk structure come into play. So you need this, basically you have to have it so that the Doppler shifting doesn't prevent inverted states from adding gain to this line. And gain in this term is the ability to have stimulated emission. But they talk about it in terms of a gain, right, in terms of the radio language. And so generally speaking, you also have polarization here, which occurs. And so polarization in laboratory is generally achieved by selecting certain modes. And so in natural masers, generally speaking, you have a polarization state. You have to have the presence of a polarization state dependent pumping, or you have to have a magnetic field that's aligning preferentially aligning the molecules to get that. But then you can get relatively high polarizations from these masers. And so because you don't have a cavity, in cavities you can have things and you can get really high gains from masers and lasers. Because it's a natural system with only one pass, you generally can't get very high gain for one particular portion. So you need some very particular astrophysical distribution of material in order to get that gain, like in megamasers. Okay, so in generally speaking, what is useful about them is, if you have sufficient sensitivity to detect them, you might see that they have sort of some velocity structure. Generally speaking, sometimes what will happen here is that for masers that are quite weak, they might not be detected, and then you also have a spectral absorption from the unpumping of molecules of the maser species in the surrounding space, which tends to suppress them. And so it can be difficult to actually detect them, even if they do exist in the internal parts of different physical situations here. So this is trying to do spatial filtering with VLBI helps in some sense, where VLBI actually filters out the wider emission automatically. One of the best uses here is to understand physical conditions of certain regions, but then also to measure the velocities of material that's traced by these masers because they're so bright. But you can also measure temperature, density, magnetic field, environments, and so forth. So these are all lots of different problems that you sort of have with them. I'm not going to go into any detail here because we're out of time, but you can read through them if you want. And then these are just a couple of examples. So this is a disk where you measure, these are sort of points where you can see the velocity structure here in the maser, and you can then trace it back to a disk. And this is a disk around an AGN. And so it looks sort of something like that. Here's another disk. This is your Synix galaxy. This is MGC 4258. And then here's a different example, which is a young protostar and sort of blowing outflow. And so you might see major emission from this outflow region. You might see major emission from the circumtotal disk. And then you might see it from a shock here. And so you can, there's lots of different places where we might expect to see it, and that can probe the structure. So this is just looking at some of the major lines at 7 millimeter here in this sort of structure. Okay, any questions, thoughts?
I have a question.
Yeah.
I was wondering if when the molecular hydrogen is used to measure the temperature, well, at the very beginning, if the different ratio of the ortho and para, the isomers of the isomers of the hydrogen could be a problem for estimating the temperature?
So for para and ortho, you're talking about water.
Sorry, I can.
Well, when you talk about para or ortho, you're talking about water. Or so para and ortho are typically for molecules. And so for the H2 molecule, there isn't really a para or ortho version of that.
Oh, okay. Okay.
Yeah, so it mostly comes back for things where you can have a different symmetry that comes about for the para and ortho. So like, I think I showed the para and ortho versions of ammonia. Where's that? Let me share the screen again. Right, so here you basically have, it's rotating this way or it's rotating this way, and you flipped it. And that is slightly different. And you might ask why it's slightly different. And it's just in terms of the rotation versus the symmetry of the molecule. You get very slight differences in how these states behave. And then here, yeah, basically you have this thing, and so you have an angle between these. And I think the para versus ortho there is exactly in what sense it ends up rotating. Because it's not basically it's not symmetric anymore. Right. Whereas molecular hydrogen is diatomic, it's fully symmetric, so it doesn't have these modes.
Okay, but that question is like in general in the cases when the ortho and para, digamos, namely affect the emission, how normally it's how normally can be treated this problem. I mean, we can assume a specific ratio of I don't know, 30% of the water is ortho and the remaining 70% is para, or we assume that all is in ortho or all is in para, or normally how can manage?
No, I mean, normally you measure both of them and you use the ratios to try and understand why there are different ratios more than anything else, right? And they trace slightly different physical, so because the transitions are slightly different, you can use the ratios to try and trace sort of more precise physical conditions, but just for that particular species, which is a little bit tricky, right? So that you can, it can allow you to pin down some things. So there, I probably speaking out of my area of expertise, but there may also be reasons why one version of a molecule might be more acceptable to form on grains versus another. So you could get depletion onto dust grains or something like that. Like so there are subtleties in understanding the astrochemistry which crop in from, these relatively small differences. For instance, you could have a magnetic field which is going through, and that might set up a certain directionality, which you then see in the line ratios.
Okay. Okay, thank you.
But the complexities are definitely out of my area of expertise at this point. So you can virtually corner Viviana and ask her about it. Any other questions?
Me.
Cece.
I didn't understand the plot in the slide 26.
Okay.
Yeah.
So what this is showing is the intensity of each J value. And so for a given, let's say you have a uniform density material, right, a gas, and you have mostly it's hydrogen with a little bit of trace CO and 13 CO and other things and dust. And so if you had a uniform density, based on the excitation, and also this thing, I think the G value right here is actually, I want to say it has to do with the intensity of the field, but now I'm blanking on exactly what G is here. But generally speaking, it's sort of a proxy for the temperature, the kinematics, or what's exciting this line. But so for a given density and a given thermal properties of that gas, you will excite a certain amount of CO 1 to 0, a certain amount of 2 to 1, a certain amount of 3 to 2. Right, and the problem is that if you say you say let's get a very dense material, and that's this green line here, and so generally speaking, you see only high excitation or mid J level lines, and then it drops down dramatically. And so the ratio between these and these are an order of magnitude, right? And you see that in actuality, the ratio between them is only a factor of 3. And likewise, if you look at the low density material, you will see that the ratio between the 3 to 2 and the 6 to 5 is again an order of magnitude. And so what this says is that what we're seeing is not homogeneous, right? And so you're seeing different density, different temperature components, which makes sense. I mean, if you have a molecular cloud, it's not going to be homogeneous, right? You're going to have a temperature gradient, you're going to have a density gradient. And so what this is probing is that structure. And it's not super trivial to fit this, or I won't say it's potentially trivial to fit this. This is only 12 points, but the problem is it's degenerate. And so you can come up with different physical scenarios which fit this identically and have different ratios of these different components. And so in general, and so people use this large velocity gradient methodology to sort of understand what the structure should be under gravitational influence, and say, okay, given this sort of model, what will we predict about the distributions of N and the distributions of the temperature and so forth. Does that make sense?
Yeah. Yeah.
Yeah. Now, you can imagine this is complex just for one molecular cloud, and then people do this for galaxies. And so the assumption is that there's one dominant thing that's contributing to here. Now I didn't show. I don't think I have. No, I don't have any slide there. But if you have, this is for a relatively low temperature cloud. If you have, for instance, a very hot source, then you would it would peak at like J of 20 or J of 30. And so you can have multiple components that are from physically different things that you then have to try and fit. Like for instance, an AGN might give you J of 20, J of 30, J of 100 levels. A Herbig Haro object, with Jet's a young protostar, might also give you J of 20, J of 30 lines. Typically, those are only probed in the far infrared, and so we don't really have any instruments that do that. So we give up. As you go to higher redshift, those lines get moved down into bands where we can see them in the ground. And so you will see some papers about high J transition lines. But obviously that's for high redshift objects, not for galactic objects.
Thank you.
Any other questions? We're well over time now.
Must astronomical mass errors be polarized?
I didn't get what your question was.
If must astronomical mass errors be polarized?
Historical masses?
Astronomical mass errors. MAS.
Masers. See. So the masers.
Measures.
Typically, they should be polarized to some extent, because you have a very preferential alignment, and so the only thing that will be depolarizing about them is that when you have the stimulated emission, that line isn't necessarily polarized in the same way that the line that came in was.
Mm-hmm.
And so in general, they won't have super high polarizations because of that. But there are certain physical situations which will end up kind of leading to something, if you have magnetic fields in there and you have orientations, and you can kind of start to get some polarization.
Okay. Thank you.
My understanding is they're not super highly, they're not like synchrotron where it's 75%, if you have pure synchrotron.
Mm-hmm.
Okay, anything else? Okay, I guess next Monday is a holiday again. The next Wednesday, we'll finish up talking about our favorite, dust, which is the nuisance parameter for most astronomers. And so, we'll finish off there. I will try to send you a final homework, which will probably be 2 or 3 questions. One about dust, one about molecules, 2 about molecules, we'll see. And so, so let's see what that, actually, I think if we have class next time, I should send it on Friday, so you have, maybe no, I think I can't remember what I put on the slide now. I wanted to give you at least a week to do it, right? So I think I don't need to assign it. I'll probably assign it on Friday, and it'll be due July 3rd. I think that's what I wanted originally, but now I'm trying to remember. So let me see what I said here. Okay, I put it at July 5th. So you guys are free for a little bit. July 5th, yeah. So I'll probably go ahead and sign this on Friday, and then have it be due 12 days after that. When is that? I can't remember. Anyway, that's when it'll be due. We also need to think about the exam. Have you thought about it at all? Do you care? When would you like it? And we're out of time, so maybe you guys can leave and we'll talk about it the first thing at the start of next class. That's good. And
the only thing we were thinking about, we talked about our, I don't know, homeworks or other exams, and the only thing that we're worried about
is having them all graded. Your presentation for trabajo de investigación.
Yeah, because nobody knows anything. even our
A mí
professors.
tampoco. Yes.
Yeah, so we really don't know if, I don't know if we come to a
Yeah.
a date and then someone has to do its presentation. So that's the
Yeah.
only thing we're worried about. But
Okay,
I
let me
think
let me
that
let me
for next-
ask actually. So I have a call with Julio right now. So let me ask there, and then we have the faculty meeting tomorrow. Oh no, wait, it's a holiday. Crap, maybe we don't. I can't remember if we have it or not because we're technically the professors are not in recess, but you guys are in recess. So I think we'll have a meeting tomorrow, and I'll bring it up there. So we'll finalize it. It'll probably be mid-July.
Okay, that
but
would
we
be
need-
amazing because with that we could like get together to get on a date.
Yeah. But yeah, no, we want to organize it outside of that, hopefully by a week. But the issue is when do we have to turn in grades? And so we need to have trabajo de investigation at least a few days before that. And then there are X number of students doing trabajo de investigation, so it's like 2 days complete.
Yeah.
So this one, okay. Yeah, so I'll try to communicate to Julio that we need to lock that down so that you
That would
guys
be amazing.
understand your lives in July.
Okay.
Okay. All right. With that, see you guys. Have a good recess. I'll see you all back next Wednesday. Yeah, we're not going to have a office hour, but you don't need one because there's no homework pending. I'm continuing to poke Priscilla. Yeah, I need to sort that out. Sorry about that. But, yeah. So that's all. Okay. Take care.
Bye.
Bye.
Bye. Bye-bye.